Hello everyone. In this lecture, we are going to revise the chapter circular motion and the rotational dynamics. Okay. So everyone write down the heading along with me. The chapter circular motion and the rotational dynamics. We are going to list down all the formulae, all the important formulae of the chapter. Okay. That will revise the chapter entirely. Okay. So let's write it. The name of the chapter is circular motion and the rotational dynamics. Circular motion and rotational dynamics. Okay, this is the chapter that we are going to revise today. Circular motion and rotational dynamics. You also write along with me and make the list of formulae along with me. The first point is the angular displacement. The first point is angular displacement. So let's write about it. Angular displacement, or the first formula that we are going to write is angular displacement. Now what is the angular displacement? Is there any direct formula? No, but there is a definition. What is that definition? The definition says angular displacement is the angle subtended by the particle performing circular motion at the center of the circle. Let us write it. Is the angle subtended by, let us make a short note as well, is the angle subtended by, angle subtended or the angle made by, angle subtended by the particle performing the circular motion, performing the circular motion at the center of the circle, right? At the center of the circle. We all of us already know this definition, right? Let me show it by the diagram. If this is the circle, this is the circular path about which the particle is revolving. Okay, let's say the particle is tracing the circle like this, and let's say initially the particle was here, and finally let's say after time equal to t, or the after time interval t, or you may be calling that time interval as delta t, no issues. The angle covered by the particle is, let's say, theta. Angle subtended by the particle or this arc of the circle at the center of the circle, that angle will be called as angular displacement of the particle in the given time interval. Okay, that's very simple thing. Fine. The next thing is angular velocity. What is the angular velocity? So next formula, write along with me as angular velocity. Angular velocity. What is angular velocity of the particle? Angular velocity is what? It is the angular displacement upon time required, right? So directly write down the formula. It is the angular displacement upon the time required. It is the angular displacement of the particle performing the circular motion, obviously, upon the time required, for that angular displacement. So again, if we go back to this diagram, and if I say for this motion from point A to B, for the motion A to B, if the particle is taking a time equal to, let's say, delta t, and let's say the angular displacement is theta, you might be calling this time required as small t. That is also absolutely fine, no issues. Or you might be calling this angular displacement as delta theta. That is also fine, no issues. But you should know what is the meaning of the symbol. Let's say the angular displacement is delta theta in time equal to, let's say, delta t, or you might be writing it as angular displacement as theta and the time interval as t. Okay, this t is not the time instance, this t is time interval. This theta is not the angular position, it is the angular displacement. Okay, fine. Now you might be writing the angular velocity as omega. Okay, now if you want to write the average angular velocity, then what you will do? You will write average angular velocity as total angular displacement upon total time required. Okay, but if you want to write the instantaneous angular velocity at a given time instance, what is the angular velocity of the particle revolving in the circle, then what you will do, at that time instance you will allow the particle to move by very small angular displacement, let's say d theta, and let's say the time required for that displacement is dt. Okay, at given time instance you will take a very small time interval, and in that time interval you will allow the particle to move by the angle d theta. Then that angular displacement upon time will give you instantaneous angular displacement. Okay, the next thing is angular acceleration. Next thing is angular acceleration. What is the formula and the definition for angular acceleration? Let's write angular acceleration. Angular acceleration. What is angular acceleration? Angular acceleration is change in angular velocity upon time required. Change in angular velocity upon time required, or rate of change of angular velocity. Change in angular velocity, change in angular velocity upon time required, for that change upon time required. Now you can write the average angular acceleration. The symbol for the angular acceleration is alpha. Average angular acceleration will be total change in angular velocity upon total time required. Total change in angular velocity upon total time required. And if you want to write instantaneous angular acceleration, then you will write instantaneous change in angular velocity, means instantaneous in the sense at given time instance you will allow the object to move for time interval equal to dt, very small time interval dt. In that small time interval there will be very small change in angular velocity. So that change in angular velocity upon the time required will be instantaneous angular acceleration, right? Fine. Now the next point that I am going to write is equations of motion with uniform angular acceleration. Just like equations of motion with uniform linear acceleration or a constant linear acceleration, let us write the next point as equations of motion with uniform angular acceleration. Uniform angular acceleration. Equations of motion with uniform angular acceleration. Fine. What are the equations of motion that we can use for uniform angular acceleration? Let me tell you about the equations of motion which we use for the constant linear acceleration. We use these equations: v is equal to u plus at, right? S is equal to ut plus half at square, right? And v square is equal to u square plus twice s. These are the equations which we use. Okay, and these equations will be used only if the acceleration, linear acceleration, is constant. Constant in direction and constant in magnitude. Only then these equations are applicable. Similar to that, just like final linear velocity, here we have final angular velocity, initial linear velocity, initial angular velocity, plus linear acceleration a, angular acceleration alpha, time interval t. Okay, just convert the linear quantities into the angular quantities. Linear velocity, final linear velocity, final angular velocity, initial linear velocity, initial angular velocity. Okay, linear displacement, angular displacement. Now we will write the angular displacement as theta. Okay, initial angular velocity u will be replaced by omega 0, into t, time interval as it is, plus half as it is. Linear acceleration a, angular acceleration alpha, time interval square. Now v square equals u square plus twice s will be replaced by what? V square means omega square, u square means omega 0 square, plus twice a means alpha, s means angular displacement. Okay, these are the relations which can be used for motion with the uniform angular acceleration. This alpha is constant. All these equations are applicable only if alpha is constant. Okay, so what is this omega? Omega is final angular velocities. Omega is final angular velocity. What is omega 0? That is initial angular velocity. Omega 0 is initial angular velocity. What is t? Sir, t is time interval. It's not time instance, it's time interval. It's time interval. What is alpha? Constant angular acceleration. Constant angular acceleration, right? These are the things which we already know. Just make a list of formulae. Then the next thing that we are going to write is, or the next checkpoint that we are going to write in this list of formulae is the relation between linear velocity and angular velocity of a particle performing the circular motion. Just write relation between linear velocity and angular velocity, relation between linear velocity v and the angular velocity. Let me write the short form VEL for the velocity. What is the relation? We know if the particle is there which is performing the circular motion, then let's say at given position, if we want to draw its direction of linear velocity, then we know linear velocity is always tangential to the path. So at this point linear velocity will be this, tangent to the path. So that velocity is, let's say, v as a vector, v bar. Let's say its position from the center will be given by the radius vector. Its position from the center will be given by the radius vector, that will be r bar, and at that instance of time the angular velocity of the particle is, let's say, omega. Okay, of course omega is a vector. It's an axial vector. If the particle is rotating anti-clockwise, then omega is coming out of the board. So this dot is actually representing the vector which is coming out of the board. Okay, so this omega is a vector. So what is the relation between v bar, omega bar and r bar? What is the scalar relation between them? That is v is equal to r omega. That is the scalar relation between them. And if you want to write the vector relation between the v bar, r bar, v bar, that is the velocity vector, r bar, that is the position vector of the particle, and the omega bar, that is the angular velocity of the particle, the relation is very simple. That is v bar is equal to omega bar cross r bar. Okay, the angle between the omega bar and r bar, you can verify here. Omega bar is coming out of the board, r bar is lying in the board, so angle between omega bar and r bar is 90 degree. Okay, so its magnitude will be omega into r into sine 90, but sine 90 is plus 1, so omega into r or r omega. Okay, what I write is this. When I write the scalar form, I write the sequence in such a way that the sequence gets reversed in the vector form. This becomes easy for me to remember. Okay, v is equal to r omega, and v bar is equal to omega bar cross r bar. I just reverse the sequence while writing the vector form. In this way I remember it. Okay, this is going to be the vector form. Which is relating the linear velocity, angular velocity and the radius vector. And you may remember this relation, v is equal to r omega. Yes, v is equal to r omega. This relation we already know. Okay, now what is the relation between the tangential acceleration and angular acceleration? Write down. Next point, relation between linear, let us write tangential acceleration. Let us not write it as linear acceleration. Let us write it as tangential acceleration. Relation between tangential acceleration and angular acceleration. Relation between tangential acceleration and angular acceleration. What is that relation going to be? The relation is very simple. AT is equal to, T stands for tangential, AT is equal to, A means acceleration, tangential acceleration is equal to R into alpha, where alpha is the linear acceleration. So let me draw the diagram corresponding to that. Okay, What is the task of tangential acceleration? The tangential acceleration changes the magnitude of velocity. Always remember, the tangential acceleration changes only the magnitude of velocity. The direction of velocity is changed by the radial acceleration, that is different, or the centripetal acceleration, that is different. Centripetal acceleration changes the direction of velocity and the tangential acceleration changes the magnitude of velocity. All right. So that tangential acceleration will be along the tangent. It might be in the direction of velocity or might be opposite to the direction of velocity. Let's say the particle is moving anti-clockwise, and if its velocity is increasing in magnitude, if the velocity of the particle is increasing in the magnitude, in that case the tangential acceleration will be in the direction of velocity. Or if the magnitude of velocity is decreasing, then it will be opposite to the velocity, like this. Opposite to the velocity, like this. Okay, let us assume the direction of tangential acceleration as in the direction of velocity, so that magnitude of velocity increases with time. So this is the tangential acceleration. Now again, the position vector of the particle, that is r bar, and let's say the angular acceleration alpha is like this. Okay, this is the scalar relation, at is equal to r alpha, that we know. And what is the vector relation between them? At bar is equal to alpha bar cross r bar. You might again recognize that when I write the scalar form, I just write the sequence in such a way that it gets reversed in the vector form. At bar is equal to alpha bar cross r bar. At is equal to r alpha, but at bar is equal to alpha bar cross r bar. So this is going to be the scalar form of the same equation, or the magnitude form, and this is the vector form. This is the vector form. Now what is the magnitude of the cross product? Alpha into r into sine 90. Why the angle is 90 between alpha bar and r bar? You can identify this. Alpha bar is coming out of the board. It is a anti-clockwise vector. It is an axial vector. Alpha bar is coming out of the board and r bar is lying in the board. So alpha bar and r bar, angle between them will be 90. Okay, so alpha into r into sine 90. Sine 90 is 1. So alpha into r. Sequence does not matter if you are writing the magnitude. So instead of writing alpha into r, I am writing r alpha. So what I remember is at is equal to r alpha. And you should also remember at is equal to r alpha. This relation is important. Okay, next. Now let us write about the radial acceleration. Okay, let us write about the radial acceleration. Also let me write one more thing here itself. What is the task of this tangential acceleration? It changes the magnitude of velocity. So I am not writing v bar, I am writing only v. So tangential acceleration you can write dv by dt, rate of change of velocity. Of course, rate of change of magnitude of velocity. Okay, you may write down this formula as well. That's the relation between velocity and the tangential acceleration, rate of change of velocity, of course in magnitude only. Okay, the task of tangential acceleration is to change the magnitude of velocity, nothing else. Okay, next let us write about the radial acceleration. Write down radial acceleration. This is the acceleration which is along the radius and perpendicular to the velocity of the particle. What are the formulae for radial acceleration? The formulae for the radial acceleration is v square upon r omega square and v omega. V square upon r omega square and v omega. These are the three formulae which are used for the radial acceleration. Of course in magnitude we are writing this. Okay, what is the task of radial acceleration? As the radial acceleration is always going to be the perpendicular to the velocity, this radial acceleration is always going to be perpendicular to the velocity. So its task is to change the direction of velocity. Without radial acceleration, circular motion is impossible, because if there is circular motion, then it means that you are going to change the direction of velocity, and to change the direction of velocity you always need the radial acceleration. Okay, it is of two types. Radial acceleration is of two types. One is centripetal acceleration and another is centrifugal acceleration. All of us already know. Just write centripetal acceleration. Centripetal acceleration, it is the acceleration which is towards the center of the circle, along the radius and towards the center. Centripetal acceleration. And the second is the centrifugal acceleration. Second is the centrifugal acceleration. This is the acceleration which is along the radius and away from the center of the circle. Centrifugal acceleration. Okay, make a list of formulae along with me. Now for this type of radial acceleration I will write Cp. Cp stands for centripetal acceleration. Okay, now centripetal acceleration I will write it in vector form. Its magnitude will be v square upon r, but its direction will be towards the center. So towards the center means minus r cap. Now what is this minus r cap? R cap is a unit vector which is away from the center of the circle. R cap is a unit vector which is away from the center of the circle. Let me draw it here. Let me draw it here. Now at a given position, let's say this is the r bar. Let's say this is the r bar. This r bar vector is the position vector of the particle which is always away from the center. So r cap is a unit vector in this direction. I should have written r cap. So r cap is a unit vector which is always away from the center. Okay, but minus r cap will be the vector which will be towards the center. So centripetal acceleration will be minus of v square upon r into r cap. So magnitude will be v square upon r, that we have written here, and minus r cap for what? Minus r cap is a vector which is towards the center of the circle, right? You might replace this r cap by what? This minus as it is, r as it is. A unit vector can be replaced by a vector upon its magnitude. So vector is r bar, its magnitude is r. Okay, so the final formula for this you might write as minus of v square, this r bar as it is, sorry I should have written r bar, upon r into r, that will become r square, right? So you might have seen this formula before. Okay, we write this unit vector as vector upon its magnitude. Okay, similarly you might write other forms of this centripetal acceleration like this. Other forms will be r omega square is the magnitude, but now you can write the centripetal acceleration magnitude r omega square, it is towards the center. So I might write it as minus of r bar, because r bar is always away from the center and minus r bar will be always towards the center. Okay, and in this formula, again this formula you might also write in the vector form. First of all, write down the magnitude which is v omega, and it is always towards the center. Now again you will write minus of v omega into r cap, okay, where r cap is a unit vector. Now again you might write here, or you might write here the centripetal acceleration in the vector form. We know it is v omega, in magnitude we know it is v omega, and in the vector form you may write it as omega bar cross r bar. Okay, you can apply the rules of cross product and you can verify that the centripetal acceleration is, just reverse the sequence and write the cross product, omega bar cross v bar. It is omega bar cross v bar. These are the different forms which you may remember. Okay, now similarly for the centrifugal acceleration, only change is the direction. The direction of the centrifugal acceleration is always away from the center. So the centrifugal, ACF, CF stands for centrifugal. We will write the same formula, magnitude is v square upon r, and the direction is away from the center. Away from the center direction can be given by r cap. Okay, now again you can replace this r cap and you can write this, that r cap as r bar upon r, vector upon its magnitude. Unit vector can be written as vector upon its magnitude. So v square upon r into r cap. R cap you will replace by vector upon its magnitude, and the final formula will again become v square into r bar upon r square. Similarly other forms, only just change in the direction. Centrifugal acceleration will be equal to its magnitude r omega square, its direction is away from the center, so here you may write r bar. Of course all of these are vectors, so write down these vector. Okay, and the final formula v omega, centrifugal acceleration v omega, that will be away from the center. So for that you have to reverse this sequence again, because centripetal acceleration is towards the center, and for that we have written omega bar cross v bar. So here that will be v bar cross omega bar. Okay, in this way you can write it. Okay, so these are the relations for the centripetal and the centrifugal acceleration. Okay, just try to remember these magnitude relations. Okay, vector relations we can derive or write as per the need. Next, The next thing is centripetal or centrifugal force. Let us write the centripetal or centrifugal force which is acting on the particle which is revolving in the circle. So write down centripetal and centrifugal force. Centripetal and centrifugal force. Of course, we will write the magnitude. Okay. In magnitude, we know it's centripetal force is a force which is towards the center, and centrifugal force is the force which is away from the center. Okay, along the radius and away from the center. In magnitude. So how we are going to write? We will simply write centripetal or the centrifugal force. We are writing just magnitude. So FCP, centripetal force, equal to centrifugal force, which is equal to mass into acceleration. So any formula you may write. Acceleration, for acceleration you may write v square upon r. Radial acceleration is what? V square upon r. Or you may write mass into acceleration. Now for acceleration, here we have written v square upon r. Now we will write r omega square. Okay, so mv square upon r, mr omega square, and mv omega. V omega is a radial acceleration, r omega square is a radial acceleration, v square upon r is a radial acceleration. Just multiply the acceleration by mass. Mass into acceleration, mass into acceleration, mass into acceleration will give you magnitude of centripetal or centrifugal force. Okay, mv square upon r, mr omega square, and mv omega. Okay, so that was about tangential acceleration and the radial acceleration. Now let us write the total linear acceleration in the circular motion. Whenever there is a circular motion, we know there are the basic two accelerations which are acting on the particle. One is the radial acceleration, or you may now directly call it as centripetal acceleration, which is towards the center, which has a task given as changing the direction of velocity. Okay. Only if you are going to consider the accelerating frame of reference, and in that accelerating frame of reference, if you are going to consider the pseudo force, in that case you are going to write down this centrifugal force. Okay. Note that centripetal force and centrifugal force are acting on the same particle. Okay, they do not form the action reaction pair. For action reaction pair to be formed, we need two forces which are equal in magnitude, opposite in direction, and acting on two different objects. But here the centripetal and centrifugal force act on the same object. Okay, and the centripetal and centrifugal force do not form the action reaction pair, because action reaction pair is formed if the action is on the first object and the reaction is on the other object. Okay, so always remember, centripetal force and centrifugal force do not form the action reaction pair. So let's say this is the centripetal force, or let us write this as a centripetal acceleration, ACP, and let's say this is the tangential acceleration. Okay, so what is the total linear acceleration? Write down total linear acceleration of a particle performing circular motion. Total linear acceleration. Total linear acceleration. Now the resultant of these two, okay, you can find out the magnitude of resultant just by Pythagoras. Why? Because the angle between these two vectors is 90. So to find out the magnitude of resultant, you can use the Pythagoras. And in the direction, to decide the direction, you can draw the parallelogram or the rectangle here. In this case, just complete the parallelogram and draw the common diagonal. That will give you the resultant of these two vectors, ACP and AT. So this vector A bar is the addition of ACP, that is centripetal acceleration, plus this tangential acceleration. This vector you may draw it here. This vector you may draw it here. So ACP bar plus AT bar. And if you want to find out the magnitude of the resultant of these two vectors, we know magnitude of resultant is, how to find out magnitude of two vectors? Very simple. If you know the angle between these two vectors, then magnitude of first, just like let's say P and Q are the two vectors and angle between them is theta, then what is the magnitude of resultant? Under root P square plus Q square plus 2PQ cos theta. Just like magnitude of first vector square plus magnitude of second vector square plus 2 into magnitude of first vector into magnitude of second vector into cos of angle between them. What is the angle between them? The angle between them is 90. So I said, as the angle between them is 90, you could have directly used the Pythagoras theorem, ACP square plus AT square, because cos 90 is going to be 0, 0 into anything is going to be 0, this entire term is going to be 0, so you could have written directly ACP square plus at square. Okay, and as per the need you can replace the values of centripetal acceleration and the tangential acceleration. Those formulae we have already seen. Okay, fine. Next, now we will write the formulae for uniform circular motion. Okay, now we will write the formulae for uniform circular motion. So here the acceleration will be 0. Which acceleration? Angular acceleration will be 0. So write down uniform circular motion. Uniform circular motion. Uniform circular motion. In the uniform circular motion, magnitude of velocity, I am not writing v bar, I am writing v. You may write omega bar, no issues. Omega bar, you may write omega, no issues. Magnitude of omega, direction of omega, and the magnitude of linear velocity, these things are going to be constant. When we say omega bar, no need to separately say omega, okay, because omega bar is constant. That means omega is constant in magnitude and constant in direction. If we are saying a vector is constant, it is constant in magnitude and it is constant in direction as well. Okay, that thing we already know. So what is the characteristic of uniform circular motion? In uniform circular motion, the speed of the particle is constant, the angular velocity is constant. Okay, next, here the tangential acceleration will be equal to 0. Why? Because the magnitude of velocity, that is the speed of the particle, is not changing. So tangential acceleration is 0. Here linear acceleration will also be 0. Why? Because omega is not changing. Omega is not changing. Okay, now we know v is equal to r omega. V is equal to r omega. V is constant, omega is constant, r is constant in magnitude, radius of the circle is also constant in magnitude. See, I am writing the magnitude of velocity. V is equal to r omega, which is constant. V is constant, so r omega multiplication is going to be constant. Okay, just write the relations which are applicable for uniform circular motion. Okay, now if we want to find out the period of a circular motion, if you want to find out period of uniform circular motion, okay, every circle will be covered in the equal interval of time. All the circles will be covered in the equal intervals of time. Okay, first circle, second circle, third circle, fourth circle, fifth circle, every circle will be covered in the equal interval of time. Every circle will be covered in the equal interval of time, and that time interval we can find out very simple. Time is equal to distance upon speed. What is the distance covered by the particle in one circle? That is the circumference, 2 pi r, upon speed v. Okay, now we know v is equal to r omega. So you may write here v is equal to r omega, r cancel, and the final formula for the time period will become t equals to 2 pi upon omega, right? We know this for uniform circular motion. You know this r cancel, this 2 pi upon omega, right? So that is the relation for time period of circular motion. So write down here time period as a heading, or simply period or time period of circular motion. Of course the motion should be uniform. For that the speed should be constant. Yes, velocity is changing in the direction, and that direction is changed by which acceleration? The centripetal acceleration, the radial acceleration, or the centripetal acceleration. Okay, that centripetal acceleration is changing the direction of velocity. Okay, but velocity is not changing its magnitude. Okay, tangential acceleration is 0, right? Tangential acceleration is 0, so magnitude of velocity is not changing, but the direction of velocity is changing, right? So t equals to 2 pi upon omega. Now what is the frequency of revolution? That is number of revolutions per second. We know frequency is equal to reciprocal of time. So frequency is equal to 1 upon time. 1 upon time means omega upon 2 pi. That will be equal to omega upon 2 pi, right? Or you may write the relation between omega and f. What is the omega? Angular velocity. Omega is called as angular frequency or angular velocity. Always remember this, angular velocity or angular frequency. What is the unit of omega? It is radian per second. Omega unit is radian per second, and unit of this frequency is what? Unit of this frequency is rotations per second, rpm, or rotations per second, rps, or rotations per minute, rpm. Okay, what is the angular frequency or the angular velocity? Angular frequency or the angular velocity omega in terms of f, this omega is equal to 2 pi f. F is equal to omega upon 2 pi, and omega is equal to 2 pi f. Always remember this. omega is equal to 2 pi f. These are the relations which are applicable for uniform circular motion. Now similarly, in terms of time period, you can observe this omega is equal to 2 pi upon t. Omega is equal to 2 pi upon t. These are the relations which we already know, right? Next, now let us write the net acceleration for uniform circular motion. We know the tangential acceleration is 0, so the net acceleration is going to be only the centripetal acceleration. So write down net acceleration for uniform circular motion. We know its magnitude is going to be equal to at square plus ar square, radial square or centripetal square, radial acceleration or the centripetal acceleration. Tangential acceleration is 0, so 0 square plus centripetal acceleration square. So the net acceleration in the uniform circular motion is the centripetal acceleration. The net acceleration in the uniform circular motion is the centripetal acceleration, or you may call it as radial acceleration, no issues. Okay, so this is the only acceleration which is present in the uniform circular motion. So note that uniform circular motion is also an accelerated motion. Okay, don't get tricked by this word uniform. Don't get tricked by this word uniform. That doesn't mean there is absence of acceleration. Acceleration is present there. Which acceleration is present? The radial acceleration or the centripetal acceleration is present there, which is changing the direction of this velocity. Okay, the tangential acceleration is absent. Fine. So in this video we are going to stop at this point. In the next video we will start from the next point, that is the non-uniform circular motion. Okay, so chalo, bye bye everyone. Let me end this video at this point. Okay, have a good day. Chalo, bye.